So we're going to discuss the ideas of concavity and the second derivative test in this section. And the best thing that we could do is to start off with a definition of concavity. And here's what they tell us in the book. They say let f be some differentiable function on an open interval I. The graph of f is said to be concave upward on that interval if f prime is increasing on the interval and f is increasing on the interval and concave downward on I if f prime is decreasing on the interval. So let's take a look at a function right here. This first one, we're going to call this one f of x. So here's f in blue, f of x in blue. Okay. If we look at this function right here, we would call this shape concave up. And the reason we would say it's concave up is that when we look at our derivative, f prime, on that same interval, up to this point, of course, we know that where the derivative is positive, the function's increasing. Where the derivative is negative, the function's decreasing. But more to the point right here, we're looking at the effect of the second derivative. And the second derivative here in red gives us a positive value for f prime, which means that f prime is increasing on the interval. Well, it certainly makes sense for us to call this shape concave up. It looks like a bowl facing upwards here, at least in this particular drawing. And we could even state that it looks a little bit as if we were to look at the values of the slope of the lines tangent to the curve over this interval, the derivative is increasing. That is, it's going from being something negative to being something positive on the interval. So we'll call this shape concave up based on the definition. We look at this shape right here. Here's f of x again. If it were concave down, of course, we would say that this is the interval over which f prime is decreasing. Right? And when we compare that to our second derivative, f double prime right here, we see that f double prime is negative on this particular interval, where it was positive on this interval. And we see where the f prime is negative, f double prime is negative. That's not f of h. Silly marker. F double prime is less than 0. We see that certainly it looks as though the shape is concave down. And looking at the slopes of the line tangent to the curve over this interval, the value of those slopes decreases as we go from left to right. So we call this shape concave down. So now, if we're looking at these shapes, we might wonder, well, what good will any of this do if we're looking at a function? So we should be able to judge when we've got a concave up shape or concave down shape without even having to go to the graph. So let's talk about this test for concavity that they give us. They tell us let f be a function whose second derivative exists on an open interval I. We'll say that f double prime is greater than 0 for all x and I. If that's true, then the graph of f is concave upward. Well, if the second derivative is less than 0 for all x in that interval I, then the graph of f is concave downward, just as we illustrated. So let's go through an example here to illustrate this point. Let's say we want to determine the open intervals on which the graph is concave upward or concave downward. So let me get out my trusty example page right here. Let's work it out. If we're going to use our second derivative, of course, we have to find the second derivative, assuming it exists, and in this case it does. Y prime, we take the first derivative, we're going to get negative 3x squared, the derivative of x cubed, and plus 6x, the derivative of 3x squared, plus 0, the derivative of that constant. And then we look at the second derivative, so we'll take the derivative again. The derivative of the derivative becomes negative 6x plus 6. So now we might ask, where is f double prime of x greater than 0? So we would say that the second derivative is greater than 0 whenever the expression negative 6x plus 6 is greater than 0. That's not a hard one to solve. We remember solving inequalities. We could subtract 6 from both sides and find that negative 6x is greater than negative 6. And if we divide by negative 6 to isolate x in this case, of course we change the direction of the inequality symbol. And so whenever x is less than 1, we're going to have a concave upward shape. Conversely, y double prime will be less than 0 for the same reason. If we set negative 6x plus 6 less than 0 and solve our inequality, we find that x is greater than 1. So we're going to say that this function would be the kind of function that has a shape that is concave up on the open interval from negative infinity to positive 1, and concave down on the interval from 1 to positive infinity. Let me just correct that here, because that looks awful. To 1 here. Okay, so we know where our shape is concave up and concave down, and we don't even really need the graph to get that information. More to come.